Cardiovascular disease remains one of the leading causes of mortality worldwide, yet the predictive models we rely on are only as trustworthy as their calibration. On this occasion, my name is Arin Agista Sugeng alongside Adriel Agustinus G, and we are presenting our work on statistical calibration analysis of complex models applied to cardiovascular datasets. Cardiovascular disease, or CVD, remains one of the leading global health problems. Based on research, CVD caused around 20.5 million deaths worldwide in 2021. Around 80% of CVD-related deaths occur in low and middle-income countries. The number of people affected by CVD is also estimated to increase by 90% between 2025 and 2050. In 2023, CVD cost around $437 million, which was the highest number recorded since 1990. Because of this burden, early and reliable prediction is very important. However, early CVD diagnosis is still challenging, especially in screening programs. Conventional methods such as ECG and lipid profile analysis are useful, but they still need additional support for early risk prediction. This leads to the research gap. Many previous studies mainly focused on predictive performance such as accuracy and outlook. However, high outlook alone is not enough to prove that one model is truly better. Therefore, this study also considers statistical significance, calibration, and probability reliability. Based on the gap mentioned before, this study focuses on comparing simple and complex machine learning models for CVD risk prediction. The models used are logistic regression, decision tree, random forest, and XGBoost. Logistic regression and decision tree represent simpler and more interpretable models. Meanwhile, random forest and XGBoost represent more complex and simple models that can capture nonlinear relationships and feature interactions. The main contribution of this study is that the evaluation is not limited to performance. We evaluate the model using outlook, accuracy, precision, recall, and F1 score. Then we use the DeLong test to check whether the outlook differences between models are statistically significant. We also use calibration analysis, including prior score, calibration intercept, and calibration slope, to evaluate whether the predicted probabilities are reliable. Finally, interpretability analysis is applied using logistic regression coefficients, odds ratios, and feature importance. So the main objective is to determine whether complex models provide meaningful advantages over simple models, not only in terms of performance but also statistical significance, calibration, reliability, and clinical usefulness. These are the related studies in cardiovascular disease prediction. This study used several previous work to see what gap can be filled. As stated before, our study aims to fill this gap by combining outlook evaluation, DeLong test, calibration analysis, and interpretability analysis. This allows us to evaluate not only which model performs better, but also whether the improvement is statistically meaningful and clinically reliable. And this is the methodology. First, we use the cardiovascular disease dataset, which contains clinical information from patients. Then the dataset is split into training and testing data with an 80-20 ratio using stratified splitting, so the class distribution remains balanced. After that, the data goes through preprocessing, including removing duplicates, dropping columns, converting age to years, and applying scaling for logistic regression. Once the data is ready, we train our 4 machine learning models. The models are then optimized using grid search and 5-fold stratified cross-validation. Next, model performance is evaluated using several metrics such as accuracy, precision, recall, F1 score, outlook, prior score, and confusion metrics. To ensure that the performance differences between models are statistically meaningful, we apply the DeLong test. Finally, model interpretability is performed to make the prediction results easier to understand, using coefficients and odds ratios for logistic regression and feature importance for tree-based models. This table summarizes the detailed performance comparison of all models. XGBoost and random forest consistently achieved higher scores across most evaluation metrics, while the low standard deviation values show stable performance across cross-validation folds. Logistic regression and decision tree perform slightly lower, but they remain important as simpler and more interpretable models. Overall, the results indicate that ensemble models provide better predictive performance for cardiovascular disease risk prediction. Based on the evaluation results, XGBoost achieved the best overall performance, with the highest outlook of 0.8026, accuracy of 0.7365, and F1 score of 0.7214. Random forest followed closely with an outlook of 0.8018, while logistic regression and decision tree still showed competitive performance. In terms of reliability, XGBoost also had the lowest prior score, indicating better probability estimation. Therefore, XGBoost can be considered the strongest model in this evaluation.
So now, in this section, I will explain the main results of the model evaluation. The main finding of this study is that the ensemble models perform better than the baseline models in predicting cardiovascular disease risk. In this study, the ensemble models are random forest and XGBoost, while the baseline models are logistic regression and decision tree. Based on the ROC score, XGBoost achieved the best performance followed very closely by random forest. This means that XGBoost had the strongest ability to distinguish between healthy patients and patients with cardiovascular disease risk. The confusion matrices also showed that logistic regression produced more false negatives, which means more sick patients were predicted as healthy. Meanwhile, decision tree produced more false positives, meaning some healthy patients were predicted as sick. Overall, XGBoost was the best performing model, while random forest also showed strong and balanced performance. And next, I will explain the model comparison based on the DeLong test. The DeLong test was used to compare the ROC values between pairs of models, and this test helps to determine whether the difference between two models is statistically significant or only caused by random variation. Now, based on the results, the difference between logistic regression and decision tree was not statistically significant, with a p-value of 0.158. This means that decision tree was not statistically better than logistic regression. However, random forest and XGBoost both showed that it has significant improvements compared to logistic regression and decision tree, with p-values below 0.001. This means that the ensemble models perform significantly better than the baseline models. XGBoost was also significantly better than random forest with a p-value of 0.025. However, the ROC difference was very small, so the practical improvement was limited. In this section, I will explain the model calibration results. The calibration is important because a clinical prediction model should not only classify patients correctly, but also provide reliable probability estimates. For example, if a model predicts a 70% risk, the actual observed risk should be close to that value. Based on the calibration curve, all models generally follow the perfect calibration line, and this means that their predicted probabilities were relatively consistent with the actual outcomes. However, logistic regression showed more deviation, especially in the lower and middle probability range. The Breyer score results also support this finding. XGBoost and random forest achieved the lowest Breyer score, around 0.182, followed by decision tree and logistic regression. Overall, XGBoost and random forest provided the most reliable probability predictions, although the difference between models were relatively small. Lastly, I will explain the model interpretability results. Interpretability is important in clinical prediction because we need to understand which features contribute most to the model's prediction. For logistic regression, interpretability was analyzed using coefficients and odds ratios. The most influential feature was systolic blood pressure, or APHI, with the highest positive coefficient and an odds ratio of 2.5573. This means that higher systolic blood pressure was strongly associated with higher cardiovascular disease risk. For the three base models, including decision tree, random forest, and XGBoost, interpretability was analyzed using feature importance. Across these models, APHI was consistently the most important feature. Other important predictors were cholesterol, diastolic blood pressure, and age. Overall, the interpretability results showed that blood pressure, cholesterol, and age played the biggest roles in predicting cardiovascular disease risk. In conclusion, this study shows that ensemble models, especially XGBoost and random forest, perform better than simpler models in predicting cardiovascular disease risk. XGBoost achieved the best overall result with the highest test ROC, while random forest showed very similar and stable performance. However, the best model should not only be chosen based only on ROC or accuracy. Calibration and interpretability are also important, especially in clinical prediction. The calibration results showed that all models were reasonably reliable, while feature importance analysis showed that systolic blood pressure was the most important predictor. Although XGBoost was the best predictive model, logistic regression remained important because it was simple, transparent, and easy to interpret. Therefore, model selection in clinical practice should consider predictive performance, calibration reliability, interpretability, and practical usability. And here are the references that we use in this research. That's all for our presentation. I hope that this research can bring new insights to the future. Thank you very much.